Okay, so this is the review session for EGME 442, Computational Cardiovascular Engineering for Midterm 2 in spring 2021. Okay, so I looked at the poll on Canvas right now, and it looks like the two most requested topics that I cover today are going to be impedance of vascular networks and the 1D equations. Okay, and so I plan on covering those two today, and then we have time afterwards. Then just kind of because this review session is going to be a little bit unique compared to previous ones. I might do the next topic as well. Okay, but my goal is to have this be around about an hour. All right, and so because this upcoming midterm is pretty unique, at least by my standards, in that it's all going to be conceptual questions. I thought kind of the best way to approach this review session is to basically take the topics that you guys selected and then go over each of the different learning objectives that I have for you, and then just kind of talk about them a little bit more in detail. Okay. All right, so let's start with the lecture notes on impedance of vascular networks, and so this is lecture notes 10. Okay. And the first learning objective that I have listed for that is to simply define impedance and compare it to the concept of resistance. Okay. And so I think this is probably one of the most interesting aspects of this unit here, because this kind of belonged to one of the weeks where there was a lot of mathematical derivations, and so I have a hunch that that's kind of why it was selected for this review. But I think this is kind of the core of why we even went over this concept of impedance to begin with, right? And so I'm going to spend a bit of time on this learning objective because it's really important. Okay. And so let's start with kind of the back end of this learning objective here, and let's talk about resistance. Okay? And so resistance is a concept that we're very familiar with in this class, and resistance, as we know, represents the ability for the vessel to resist fluid flow in there based solely on viscous losses. It's hard to talk about resistance without actually using the word resistance. So let's see, resistance represents, let me phrase it this way. Resistance represents purely viscous viscous resistance to fluid flow. Okay. Okay. And this idea came from the fact that we know that as blood flows into a tube or any fluid actually, so this is relevant for any fluid, not just blood. Okay, we know that there's going to be some viscous shear forces that's going to pull the fluid back, right? Okay. And of course, these are most prominent near the wall, but you actually get these viscous shear stresses all throughout the fluid. And we know that viscous shear forces, they always act to impede the flow. So viscous shear never really helps the flow. Because in this situation here, the flow wants to go to the right, but the viscous shear forces are pulling it back, right? And so viscosity is the same thing as friction. And so the way that you understand friction, that's the same thing for viscosity, okay? And so when we first defined resistance, and that was given our simple R, this was the only real effect that we're actually looking at. And so, the formula that we use to denote this is that P, or I should say delta P, is equal to R times Q, right? And this is our, Ohm's law number 2 here, where, this represents the fact that in order to drive a certain amount of flow Q in a blood vessel, right, we need to have a certain drop in pressure. Okay? And that drop in pressure is going to be needed to overcome the viscous energy losses. Okay, And so when we talk about resistance, it was just purely based on viscous forces. And you know, viscosity plays a big role in this. But in reality, you know, for a flow as complex as blood flow, you know, there's a lot more going on that actually impedes the flow of blood. Okay, so let's talk about some of those other factors, and then we'll see how impedance actually takes this into account. And so some other factors that impede blood flow, let me pull it up real quick, okay? Okay. And so some other factors that impede blood flow are things like wall deformation, right? Things like inertia, okay? And things like wave reflections. And there's other smaller factors too, but this is just kind of a small list. Okay, and so whenever you have like a pulsatile flow like you have for blood, you know, we have to take all these other factors into account, because if we just consider just the viscous effects, we're going to be missing some of the the picture. Okay, and so the idea of impedance is that it takes all of these things, all these factors into account, basically anything that can you know, impede or resist the flow of blood. And the thing about these other factors here, you know, and the reason I kind of list these is that all of these things, their effects, they depend on the frequency of the oscillation. Okay, because remember, you know, our blood flow is pulsatile, and so it goes up and down, up and down, up and down. It doesn't just stay at a constant number. Okay, and so all of these extra effects here, so things like the wall deformation, the inertia, and the wave reflections, you know, those effects on the flow, they're going to depend on the frequency. Okay, and so, you know, if you have a person who's, you know, just had a cup of coffee and his heart's beating really, really fast, right? And you compare that to, you know, Michael Phelps, who just woke up from a nap, right? Whose heartbeat is like, you know, unhumanly slow, right? The effects of inertia and wave reflection are going to be very different in those two people, because the amount of inertia that the amount of inertia resistance that or impedance that you know, that the blood's going to feel is really going to depend on how quickly the heart is pumping. Okay, and so impedance kind of seeks to kind of take all of these things into account, right? And so if you're familiar with circuits, you know, if I can take just a quick aside here, you might be, you know, familiar with the concept of impedance as well, right? And so you know, when you compute impedance from a circuit, you not only just compute the resistances, but you also take the inductors and capacitors into account, right? Because you know, and I'll admit, you know, when I first learned circuits, at this point wasn't really made clear to me that, you know, the effect of an inductor and a capacitor, those things can actually impede electrical current, right? But, you know, their effect, or the way that it does it, is not exactly the same as the way that resistors do it. Okay, and so here it's exactly the same thing. And so, you know, all of these effects right here, wall deformation, inertia, wave reflections, all of these can impede blood flow, but the way that they do it is different than just viscous resistance over here. Okay. And so when you think about this learning objective of, you know, defining impedance and comparing it to the concept of resistance, you can think of impedance as kind of a bigger picture, or kind of a more complete expression for all the factors that can affect blood flow. Okay. And unfortunately, no, because it's a lot more complete, its mathematical description is a lot more complex. But that's kind of the price you pay for for a model here that's a lot more you know holistic. Okay. All right. So hopefully that makes things a little bit more clear about what impedance is and why we use it. Okay. And so the next learning objective that we have here, which for this class is a fairly minor point, but if you plan on doing more applied math stuff, this is important. Okay. And so the next learning objective is to explain what it means to linearize an equation. All right. And so this learning objective kind of takes place at kind of near the very beginning of the lecture notes for impedance. Okay. And so the motivation behind this, or why we're talking about this to begin with, is remember our starting point for this unit on impedance was to start with the 1D equations. And the thing about the 1D equations, which we'll get into later on in this review session, is that it's a really complicated PDE. Okay? It's not as complicated as Navier-Stokes, but it's still pretty complicated. Okay? Okay. And the thing with complicated nonlinear PDEs is that they're really hard to solve, right? And so in order for us to kind of start working with this equation and to derive, expressions for impedance, we couldn't just take the 1D equations as they are. And so we had to think of a way to simplify these equations, but still kind of respecting the essential physics of these equations. Okay. And the way that we did that was through linearizing the equation. And so the idea with linearization is we want to simplify, specifically, we want to simplify all the terms that are nonlinear, okay? And so what do I mean by nonlinear? And so remember, nonlinear terms, all that basically means is that we have a solution variable multiplied or divided by a solution variable. Okay. And so one example that that I showed in the lecture notes is we have partial z of 4 over 3 q squared over a. Okay. And so this term right here is very nonlinear because remember when we're solving our 1D equations, we're solving them for flow and we're solving them for area. Okay. And since here we have and so flow and area are two solution variables. And so, because we have q squared here and we divide by a, that's a nonlinear term, okay? And so I'm not going to go into the details of, how we actually linearize it. I just kind of want you guys to understand why we do it and what it actually means, okay? All right, so I don't want to dwell too much on this topic here because I think there's more important ones for us to talk about, okay? The next one is a big one, okay? Right, and so the next learning objective is to define reflection coefficient and how wave reflection can occur even in regions far from the capillaries. Okay. All right. And so this is one of the big points from this unit as well. Okay. Because we've talked about wave reflection or wave propagation a lot, especially when we talk about arterial biomechanics. But in before what we said was kind of thinking back to the analogy of the string on tied to a wall, right? In that situation, we said that the wave reflection can only occur once the wave hits the wall and comes back. Okay. Okay. Right. And so that's kind of what we previously thought, is that, if you have a wave that's coming in, okay, the only place where it can reflect is when it reaches kind of the wall at the end. And then once it hits it, then it reflects backwards. Okay. But in this unit, what we're saying is that, wave reflection can occur actually in other parts of the vessels. Okay. Right. And the parameter that defines this is known as the reflection coefficient. Okay. And so the reflection coefficient, we give that the symbol capital gamma here. Okay. And the way we define it is this. Okay. So we say that this is equal to Z0 minus ZT divided by 0 plus ZT. Okay. Okay. Where the Z0 here, that's our characteristic impedance. And our ZT here is our terminal impedance. Okay. Okay. Right. And so let's go over some differences or define what these are, because that's kind of important. Okay. All right. And so let's say that we have a vessel segment like this, okay? And the flow and the blood is going to flow through this vessel segment, okay? Right. And so when we say characteristic impedance, what we mean is the impedance to flow for just this vessel segment. Because as the fluid or as the blood flows through this vessel, then it's going to, it's going to be impeded, right? It's not going to flow just freely, right? And this is due to a combination of the viscous and the wave reflection, the inertia effects, all the stuff that we talked about at the beginning of this review session, okay? And so that's the characteristic impedance. And so that's Z0, okay? All right. And so once the blood leaves this vessel segment, there's more blood vessels after this, okay? Then, for all the vessels that are downstream of this, or, everything that's after this vessel segment, it's going to experience some more impedance, right? Okay. And so the impedance of everything that's beyond the current vessel, we'll call that ZT, or terminal impedance, okay? All right. And so that's the difference between the impedances. So you can almost think of this as like characteristic impedance is like the characteristic of yourself, right? That's the impedance of your own vessel. And then the terminal impedance is the impedance for everything that comes after you, okay? All right, and so what this reflection coefficient tells you is that, as long as you have a difference in impedance between the current vessel and everything afterwards, okay? Okay. As long as Z0 and ZT are different in some way, then you're going to get some wave reflection, okay? And it might be just a very small amount, right? It might be just, this reflection coefficient might be like 0.01, which is just a 1% reflection, right? But that's all that it takes, right? And so what the reflection coefficient tells us is that in order to get, some kind of wave reflection, all that has to happen is that you have to have a difference in impedance between this vessel and another one, okay? And so if I can illustrate this in this vessel here, let's say that we have a wave that's coming in like this, okay? And that travels along this vessel, okay? Once this wave hits this point where it hits the end of the vessel, and it sees the fact that, you know, the impedance of the vessel that I just traveled through is different than the impedance of everything that's downstream, some of that wave is going to reflect, okay? Okay, it might not be a lot, but it might some of it's going to reflect back, okay? And so maybe, you know, going forward, you know, you might have a pressure wave that looks like that may look, you know, virtually the same, okay? But coming this way, you know, you might have just a tiny little blip of a wave that goes backwards, okay? Right, and that reflected wave, that tiny bit, is due to a difference in impedance between, you know, this vessel and the next one, okay? And so that's the purpose of the reflection coefficient, and you know so that definition is not possible without this idea of impedance, okay? Okay, and so that's the third learning objective, okay? And so the fourth one here, we've actually defined most of these already, okay? Because the fourth learning objective for this unit is to define and differentiate between terminal impedance, characteristic impedance, and input impedance. Okay. And so we've already gone over terminal and characteristic impedance. So I'm not going to repeat those, but let's go over this concept of input impedance. Okay. And so input impedance, you know, we have a formula for that in the notes, but I think the formula actually makes it more difficult to understand actually. And so let me just kind of explain this just intuitively. Okay. All right. And so let me draw our vessel again. And so we know from the previous page that, you know, the impedance of this vessel itself is Z0, okay, a characteristic impedance. And then everything that comes after this is ZT, terminal impedance, okay? The input impedance is simply just a combination of both of these effects, okay? Okay. And the way to interpret impedance is, you know, let's say that you stand at the inlet of this vessel. Okay. And so let's say that you're standing at the inlet of the vessel and you're going to look down the vessel, okay? And so if you look down the vessel, then the total amount of impedance that you see is a combination of the characteristic impedance and the terminal impedance, right? Because eventually you're going to have to pass through both, right? Right. And so that's the whole idea with input impedance. And so the formula for it is given by Zi, and this is equal to ZO times 1 minus the reflection coefficient times e to the minus 2 lambda L, okay, divided by 1 plus gamma e to the 2 lambda L, minus 2 lambda L. Okay. Right. And so you can see this formula takes both of those things into account. So obviously you see characteristic impedance Z naught, okay? But then this factor right here, the reflection coefficient, you know, that takes the terminal impedance into account, okay? And so this input impedance is kind of, you can basically just think of it as just the combination between the two, okay? All right, and so the last learning objective that that you should know from this unit is basically our algorithm for finding the input impedance for a network of vessels. Okay. And so this is kind of the big algorithm that we had at the end, and this was kind of the subject of your homework. Okay. And so, I think, we looked through that process pretty in depth, the previous lecture yesterday. Okay. Um, and so let me just kind of summarize it all, or kind of summarize kind of the purpose of this, right? Because remember, with the impedance here, it's interesting to know this. If we look at kind of our cardiovascular system as a whole, it would be nice to know, what's the impedance of this entire system right here, as we kind of, as the blood kind of goes about its business. Okay. And so, in reality, you might have blood vessels that go like this. Okay. Okay. And so you have a very complicated network. Everything should be connecting, of course, right? Okay. Right. So you can draw your little like Christmas tree or snowflake or whatever you want to call it. Okay. And we want to find the impedance of this entire thing. Okay. All right. And so the way that we compute this is we use our procedure at the end of the impedance lecture notes. Okay. And it kind of goes like this. And so we kind of start at the end vessels. Okay. Okay. And we start by the end vessel by computing the terminal impedance, or maybe even the reflection coefficients at the end. Okay. Okay. Because if you know the terminal impedance, what you can do is you can combine that together with the characteristic impedance of its immediate neighbors. Okay. Okay. Compute the Z naught for the immediate parents, and then from that you can compute the reflection coefficient of that vessel. Okay. Okay. And if you can compute the reflection coefficient, you can compute the input impedance of that vessel. Okay. And then once you compute that input impedance, this input impedance now becomes the terminal impedance of this vessel's parents. Okay. Okay. And then you just rinse and repeat the entire process. Okay. And if you have cases where you have daughters in parallel, then you can combine things in parallel. Okay. But the whole idea is to continue like that. Okay. All right. And so I don't want to get too much into it because I want to make sure, because the 1D equations have quite a bit more learning objectives, and so I want to make sure that we have enough time to cover all of those. Okay. But if you want to learn more about this procedure, I would look at the lecture notes for week 14, lecture 2, because we went over in pretty good detail there. Okay. All right, and so that's all the learning objectives for the impedance lecture notes. And so if you understand these concepts, you're going to be good to go for the exam, right? And so now let's move on to the learning objectives for the 1D equations. Okay. Okay, and so for the 1D equations, let's start with the first one. Okay. And so the first one is to explain the advantages and disadvantages of using the 1D equation from a modeling perspective. Okay. All right. And so this was our first topic right after the spring break, right? And if you think about what we were covering right before the spring break, we were covering kind of two modeling techniques that were that were kind of very different from each other, right? And so on the one end of the spectrum, we had LPMs, okay? And so those were our non-parameter models. And so just to kind of jog your memory, these models were basically circuit representations of our blood flow. Okay. Okay. The nice thing about LPMs is that they're 0D, right? And so meaning they were circuits, and so there was no dimensionality involved in that. Okay. And additionally, they were governed by ODEs, or ordinary differential equations. Okay. And because of that, they were insanely quick to solve. Okay. Okay. Right. The downside of using LPMs is that they were not very accurate. And so if you're looking for something that's sophisticated to give you like wall shear stresses and things like that, then it's not going to be very reliable for that. Okay. All right. And so that's one end of the spectrum. And so the other end of the spectrum that we're looking at was CFD, right, which is what you guys are all using for your final projects. Okay. And so CFD here is CFD is a method for solving Navier-Stokes and 3D geometries. Okay. And so it's very sophisticated. Okay. Okay. And so it's basically 3D Navier-Stokes. Right. And so the benefits of CFD is that it's incredibly detailed. And so you can get things like, the pressures at a very precise location in the vasculature. Okay. Okay. It's accurate, it's high resolution, and it directly kind of represents, the vessels that you want to see, right? Because a lot of times, you're looking at these blood vessels and, they're three-dimensional structures. And so CFD allows you to look at, the flows and pressures within the structures in which it was originally designed, right? And so you don't have to do any kind of weird, how do I represent this with a circuit? Okay. The downside to using CFD is that it's very expensive, okay? And when I say expensive, I don't necessarily mean money-wise, but what I mean is that it usually takes, some kind of supercomputer to run it, or it's going to take you just a lot of time. Okay. And so you're going to pay the cost either in just waiting a bajillion years for your simulation results, or you need to have just access to a very nice computer. Okay. Which is what you guys are all doing for your final projects. You're running your simulations on a supercomputer. All right, and so these are the two methods that we had kind of before the spring break, and they kind of represent, the two extremes, and that's why I kind of put one on the left and one on the right, okay? And so sometimes, sometimes this doesn't give us, exactly what we need, because sometimes we need a solution that's fairly fast, but we want something that's more accurate than LPM, okay? And we might want a decent amount of accuracy, but we don't want to go through the whole thing with CFD, right? Because CFD requires that you build a CAD model, then you mesh it, then you run the simulation, and then something goes wrong, and you have to debug and all that stuff, right? And so sometimes CFD is like a little bit too much for what you need, okay? And so the nice thing about the 1D equations is that they kind of sit right in the middle of both of these guys, okay? And they kind of represent kind of the best of both worlds a little bit, although not being not as good as either one. Okay, and so 1D equations, they're not as simple as circuits, but they're not as sophisticated as full Navier-Stokes. Okay. Okay. They're equations. They're PDEs, but they're not nearly as complicated as Navier-Stokes. Okay. And they're still fairly quick to solve, but not as quick as ODEs, okay? Right? And so they represent kind of a nice kind of middle ground here. And actually, this middle ground has actually carved out quite a niche in the research community around blood flow, right? And so it's nice, okay? And so it's something that you can solve quickly, but it's not going to, you're not sacrificing all too much, okay? All right, and so the kind of the bigger picture question for this learning objective is, as an engineer, when you're out there, you're let's say that you're doing this kind of work out there, or even even if you're not doing something, if you're doing something totally unrelated, right? A lot of times you're going to have several different tools at your disposal to accomplish a task, right? And so no matter what that task is, you might need to manufacture something, or you might need to design something, right? And so no matter what you're doing, there's always going to be a multitude of different tools that are available to you, okay? And so part of your job as an engineer is going to be to select the best job select the best tool for the job. Right? I try to sound really cool, but I kind of failed, right? And so it's I'm introducing this idea of the 1D equations to you and kind of framing it in terms of its features, because that's kind of how you need to think about your engineering tools, right? And so when you think about your engineering tools, there very, very rarely is there, a situation where there's one tool that kind of fits with everything, right? What's more likely to happen is that, you'll have one tool and it's good for some things, but not so great at other ones. But you have another tool that might be good at some things and not so great at other ones, okay? And so when you talk about computational modeling, it's the same way, right? And so there's always going to be a multitude of different approaches, multiple of different softwares, multiple different programs that are available to you, right? And so part of your job as an engineer to say, okay, here's the task that I've been given. Here's the analysis that I have to do. What's the best tool that I have that can accomplish this in the most efficient way possible, okay? And so, there's not kind of a one size fit all, and there's not one answer to this, because you really have to think about, what are the features of this tool that I'm looking at, and what kinds of jobs is it good for? And then based on that information, you go ahead and choose the best job for that. Okay. And so that's kind of the long explanation for this first learning objective, is to kind of know, what the 1D equations are good for and bad for, and to kind of think of the situations where you would use it. Okay. All right, and so that's the first learning objective. And so the second learning objective is to explain in general how the 1D equations are derived. Okay. All right, and so this actually took up, the vast majority of our time when we're talking about 1D equations. And so, I'm not going to ask you to recreate that derivation, because that took us more than one day to do, right? But I just want you to just kind of understand the steps of just generally what are the steps accomplishing. Okay. And so generally, what we were doing to derive the 1D equations was we were starting with Navier-Stokes. Okay. Navier-Stokes, which is conservation of mass and momentum in a flowing fluid. Okay. And what we were doing was, the fact that we know that we're in a situation where we have kind of flow in a pipe. Okay. All we were doing was that, we're saying that we know that flow is going to happen in this blood vessel. Okay. And so to simplify these equations, let's take an average of the Navier-Stokes, or let's integrate the Navier-Stokes equations over the cross-sectional area. Okay. Okay. Right, and so by integrating and by doing a bunch of the math, and we finally arrive at the at the 1D equations. Okay, and so of course I'm not going to repeat that stuff here, but let me just say one key point here. Okay, And so one key point was the fact that, we're solving our 1D equations for flow, right? And so flow is given by the symbol Q, okay? Okay. And kind of key to our analysis was that, our Q here was simply just an integral of the velocity over the area of the vessel, okay? And so we use that definition repeatedly in our derivation in order to derive the 1D equations, okay? And so for the exam, or for even beyond this class, I don't expect you to memorize that derivation. I actually had to look it up again myself and kind of have it right next to me as I develop my notes. But you should kind of understand where they came from and what steps that were following. Okay. Okay, and so that's that's learning objective 2. Okay, so fairly easy with that one. All right, so learning objective 3. And so the third one here is to explain the significance of having the cross-sectional area being an unknown in the 1D equations. Okay. Okay. All right, and so by cross-sectional area, what I mean is A, right? And so that's literally just, you have the vessel like this, what is the cross-sectional area at any given time, okay? All right, and so when you first think about it, it might seem a little bit of a strange thing to have, the area being unknown, okay? Because basically what we're saying by saying it's an unknown is we're saying that cross-sectional area can change, as a function of Z and as a function of time, okay? And so what's the reason why that cross-sectional area can change? And so the main reason for that is the fact that, our walls are deformable. Okay. And so since our walls are deforming, right? And so, might look something like this, that's of course going to change the local cross-sectional area, okay? And this is one of the nicest features of the 1D equations that's really difficult to get in the other parts, is that we are able to model deformable walls, which is a key feature for blood flow. Okay, and so this is a really nice thing that we have here for the 1D equations. Okay, and the fact that the cross-sectional area is unknown, emphasizes this fact and kind of illustrates that hey, our cross-sectional area, we don't just have a rigid tube where the area is just staying the same. We actually have a deformable tube, where that cross-sectional area can kind of change just like that. Okay. All right. And so fairly straightforward one. Okay. All right. So number 4. Number 4 is to state the assumptions used when deriving the 1D equations. Okay. Oops. There. And so we're going to state the assumptions used when deriving 1D equations. All right. And so, because we're doing kind of a pretty vast simplification of the Navier-Stokes equations, we had to list some assumptions in order to do this, right? And so let me just kind of list them out very quickly here, and then we'll explain kind of what they mean. Okay. All right. So the first assumption that we make, which is a fairly reasonable one, is the axisymmetric assumption. Okay. And so axisymmetric, all that means is that we have no changes in theta. Okay. Because remember, when we're doing our blood flow equations, we like to work in cylindrical coordinates because our blood vessel looks like a cylinder, right? And so to simplify our equations, what we assume is that any derivative with respect to theta here is 0. Okay, and so that's that's a pretty key one. Okay, and so besides that, we also use some kind of standard assumptions from from Navier-Stokes just in general. Okay. And so one thing we assume, and this is something that's implied by the form of Navier-Stokes that we start with, is that we assume the flow is incompressible. Okay. Right. And so all incompressible means is that the density is constant. And so that simplifies our mass conservation of mass equation quite a bit. Okay. And so the other assumption that we usually make with Navier-Stokes is that our flow is Newtonian. Okay. And so it's viscosity. That basically means its viscosity is constant. Okay. Right. Let me see what other assumptions that we make. I think those are the main ones, right? Oh, another big one. And so one big assumption that we made later on was we had to assume a shape of the velocity profile. Okay. Right. And then for this one we basically took a page from our our Navier-Stokes solution, and we just assumed that the velocity profile was parabolic. Okay. Right. Let me just kind of make sure. I think that's it. We can talk about the boundary conditions too. Actually, I think this might be a good place to talk about that. Okay. Because that is a good assumption there. And so the first boundary condition is that we're going to assume no slip at the walls. Okay. And so that basically tells us that when the radius is equal to big R, then the axial velocity is equal to 0. Okay. Right. And so notice here we have uz. Okay. And so uz is the flow that's going down the vessel. Okay. Right. And our other boundary condition was that for the radial velocity, let's see, let me say, label this as axial velocity here. Okay. And so first boundary condition is for axial velocity. Second boundary condition is radial velocity. Okay. And so radial refers to the direction. And so radial means basically away from the center. Okay. And so the radial velocity, it has to match the velocity of the walls. Okay. And so we evaluate UR at R is equal to big R. This is equal to partial R partial T. Okay. And so just to kind of give you an illustration between UZ and UR, it looks a little bit something like this. Okay. And so UZ is the component of velocity that goes down the pipe, just like that. Okay. And UR is the direction of velocity that goes towards the wall or away from the wall. Okay. All right. And so that's learning objective 4, sorry. And so that's all the assumptions and the boundary conditions that we have. Okay. Learning objective 5, you don't have to worry about it. 5, and I should have taken this off the study guide. Okay. And so learning objective 5 basically says to derive the 1D equations. Right, so don't worry about this one. So obviously, I'm not going to ask you to derive the 1D equations on a 90-minute exam. I wouldn't even ask you to do it, outside of the exam too. Okay, so don't worry about that one. I think that was just there, just kind of I left it there by mistake. But the reason I kind of wrote that to begin with is that I want you to kind of maybe not derive these equations yourself, but just to kind of appreciate each of the steps and kind of understand what each of the steps do. Okay. All right. And so learning objective 6. So learning objective 6 is to explain why the parabolic velocity profile assumption is needed. Okay. And so this unfortunately kind of gets into the details of the derivation. Okay. But if you look into the derivation, you know, at some point we were kind of stuck. Okay. Okay. And the place that we were stuck was that we kind of were stuck having to evaluate a term that looks like this. Oops. Okay. And so we had 2 pi times partial z of integral of 0 to big R of uz squared r dr. Okay. And so we were kind of stuck on this term because, you know, there wasn't really anything we can do about it. Okay. Because all the other times that uz appeared in our derivation, we were able to convert it to flow by saying that, you know, the integral of z uz is equal to flow, right? But we couldn't do that for this one because we don't have integral of uz. What we have here is integral of uz squared. Okay. And so we were kind of stuck because we couldn't really evaluate this term or simplify it anymore. Okay. And so in order to evaluate this term, we had to kind of plug in something for uz. Okay. Right. And so in order to plug in something for uz, you know, we kind of need to know what uz looks like, right? And so what we did was we kind of took our solution from, you know, Navier-Stokes, the steady case, you know, way back near the beginning of the semester, and we plugged in an expression for that here, and then from there we were able to continue on with the derivation. Okay. All right. And so I won't get into, you know, any more details than that because, you know, you're not going to need it for the exam. You know, that's kind of the reason why we had that parabolic velocity assumption, is because, you know, we had this integral of velocity squared, and we needed to plug in something for the velocity in order to move forward with the derivation. Okay. All right. And so that's the 6th learning objective. And so we have 2 more to go. Or technically only 1 more because the last one doesn't count for this exam. Okay. And so the 7th learning objective is to define constitutive model and explain why we need one when deriving the 1D equations. Ooh. All right. Okay, so constitutive model, and so why do we need one? And so let me motivate that first. Okay, you know, kind of like what we mentioned before, our primary solution variables from the 1D equation are going to be flow and area. Okay. Right, which is good, which is fine. But, you know, when we're talking about cardiovascular flow and flow in our blood vessels, you know, another thing that we're really interested in is pressure. Okay. Because pressure is something that we really want to know too, right? That's one of our key variables here. Okay. And so in order to get pressure, we have to use what's known as a constitutive model. Okay. Right. And so the idea with the constitutive model is that it's an equation that someone developed, okay, which forms it forms a relationship between pressure and wall deformation. And you know, in our 1D equations, we do have a measure of wall deformation, and that measure is the area, right? And so the constitutive equation is basically, you know, a relationship that says, you know, if you have a certain area in your blood vessels, you know, then you can relate that to the pressure, okay? And so one example here, which I'll give really quick, okay, is the Kasab constitutive model, okay, which says that the difference in pressure, P minus P naught, where P naught is some kind of, you know, reference pressure, okay, this is going to be equal to E times H naught divided by R naught times A divided by A naught minus 1, okay? Right? And so the way to read this equation is to say that, you know, let's say that you have some kind of area A, okay? You're going to plug that into this equation, and you're going to have all the other terms here, okay? And then from that, you're going to be able to compute the pressure P, okay? Right? And so this constitutive model, you know, all the point of it is to basically just have a relationship which takes in area and gives you pressure, okay? Because pressure isn't something that's immediately solved for in our 1D equations, okay? And so the constitutive model basically gives us one more equation that we need in order to solve for that pressure, okay? And you have options here. And so, you know, we have different constitutive models that are developed by different people. And so you can use, you know, whichever one that you think is best for your problem. Okay. And of course, you know, we don't have the, you know, we're not able to go in depth about, you know, the different constitutive models and to see which one's good for the other ones. But, you know, that's something that you can study further. All right, and so that's the 7th learning objective, and the 8th one that I have on the study guide is also kind of it's kind of like a non-objective. Right? It's not a non-objective. It's I mean, in the grand scheme of things, this one's the most important one. But you know, it's not one that I can test you on the exam, okay? Because you know, I've only given you one 1D code in this class. And so the 8th learning objective is to apply the 1D equations to solve for flow, pressure, and area in a blood vessel. Okay. And so what this learning objective means is that, you know, you should be able to, I mean, ultimately, you know, to write a code that solves the 1D equations. Okay. Okay. And so eventually, you know, that's what, you know, that's what you should be able to do. Or not should, but you know, that's what you would want to do with this kind of information. Okay, but in reality, you know, for this class, I gave you the code that one of my colleagues had written for the 1D equation. So you know, all this learning objective is just basically to make sure that you know that you got that code, you can run it, and you can play around with that a little bit. Okay. Okay. Right. And so it's not something that, you know, not something that I can test you on the exam, because, you know, I can't write a question that said, run the code that I did before, you know, and that's not really that interesting of a question. Okay. But, you know, but, you know, the kind of the point of this learning objective is just to illustrate that, you know, all the equations that we kind of spent a long time developing, those can be, you know, transferred or transported into a code through which you can solve the PDE. Okay. And so that's kind of the only purpose of that learning objective. Okay, and so that's all the learning objectives for 1D equations. And so in terms of time, you know, we're ended up perfectly. And so this is just a little bit over an hour. Okay, all right. And so you know, hopefully this video was helpful for you guys, especially to clear up maybe some anxiety about some of these topics, because I know they're very math heavy. But you know, what I wanted you guys to get from these is not really kind of the mathematical details, but kind of just the conceptual stuff and kind of the big picture stuff. Okay. Right, and so that's it for this review session. And so if you have any more questions on this, you know, please don't hesitate to reach out. And so, you know, I'll be free to answer questions all the way up until the exam starts next Thursday. Okay. All right. So best of luck studying, everyone. And I'll see you guys next week.